panel session today is on generative design. And you may or may not be aware of generative design, but it can be defined using a number of terms, and I'm not going to define it. But you might hear, if you ask people about what it is, they might talk about an automated design process, or maybe an iterative process. They might talk about developing multiple solutions to problems that have defined constraints by a user or something like that. And you'll almost certainly hear that it is a form of optimization of design. Now, if you dig further, you might find that the person may or may not know what exactly they mean by optimization, but that's another thing that we have to delve into. So what we have for you today is a panel, and we've titled this Perspectives on Generative Design and Construction, because it's not really possible to give all perspectives. So we're going to provide 3 perspectives for generative design. One is loosely in reinforced concrete and construction, another in steel design and fabrication connections primarily. Both of those are kind of from a research perspective, and then we also have a consulting engineer who's going to provide an industry perspective. So these are our 3 perspectives, not intended to be a full coverage of the topic, but like I said, perspectives. So I think you'll find that the presentations are actually quite different. And what we'd like to do, we'll have our presentations. It'll take a little bit more than half of our hour, and then afterwards we'll open the floor to some questions. So I'm hoping that you will have some questions about what you see, and maybe we could generate a little bit of a conversation about what generative design is and what's interesting to me, what it might be in the future based on what we've seen so far. Okay, so with that, I'm going to introduce our panelists in turn, and the format of the session is going to be that we will not take any questions after each presentation, but we'll allow all 3 of our presenters to give their perspectives. Once the 3rd presentation is done, then we'll stop and take a breath, and then you'll have your opportunities to ask some questions. All right. Okay, so our first presenter, or our first perspective, perhaps I should say, is Fatima Alsakka. She's a graduate research assistant and PhD student in construction engineering and management at the University of Alberta. She holds a bachelor's degree in construction engineering and a master's degree in civil engineering from the American University of Beirut. Fatima has research interests in a variety of topics, ranging from 3D concrete printing to lean construction, construction management, and deployment of digital technologies in manufacturing facility for, construction manufacturing, pardon me. Her current work is mainly focused on building a digital twin for construction manufacturing facility for estimation and scheduling purposes, but she also finds interest in other topics that she hopes could help bridge the gap between academia and industry. Among these topics is generative design in construction, which is why she was excited about joining this discussion panel. So I'll turn it over to you.
Is it working? That's on. Huh? Switch on. Hello? Okay. All right. Thank you, Dr. Driver, for your introduction. Good morning, everyone. Many of you have known me as a caterer for the past few days, but today I'd like to be a PhD student. I'm going to share with you a few thoughts on how we could use generative design to build more economical and sustainable reinforced concrete structures. Thank you. You've already supported my presentation with so many facts. So aren't we all struggling with these heat waves we've never experienced before? In fact, if you check your weather forecast right now, you'll find there is a heat warning in Edmonton where we experience minus 40 degrees in the winter. And this is because the carbon dioxide, which is a heat trapping gas, is on the rise. And our construction industry is contributing to this. Did you know that 1 ton of carbon dioxide is emitted with every 1 ton of cement we produce? In fact, 6.11 billion tons of carbon dioxide equivalents were emitted by the manufacturing and construction sector back in 2016. And this makes cement production account for about 8% of the world's carbon dioxide emissions. Okay. And these facts accompany a growth trend in cement production. In 1995, not only, 1.39 billion tons of cement were produced compared to 4.1 billion tons of cement produced in 2020. And we have similar figures for steel production. We use steel also in reinforced concrete structures. Still, we keep seeing these concrete boxes everywhere we go. I don't see any here, but and why is that? Because we continue to use these formworks of uniform cross-section. This is although we have learned, and many of you have taught us, that loads across a concrete structure vary. They're not the same. Different points along a beam, for example, are not subjected to the same loading conditions. What does this mean? It means that we are using more material than what we actually need. And that's why, so we stop struggling with these heat waves. We need to optimize our designs in order to reduce material waste. Now, on the other hand, we often see these organic, irregular shapes in nature. So why can't we imitate these for our reinforced concrete structure? From a design perspective, we actually can, with the help of the concept of generative design. Very briefly, what does generative design mean? It means that we use computing powers or artificial intelligence to generate design alternatives that meet a certain set of design goals and parameters that we set. And the goal is to use exact amounts of material only where they are needed. This, however, produces complex shapes that are basically too complex to build using our traditional form-based construction. Fortunately, there is the concept of, or the technology of 3D concrete printing, which enables the construction of such organic and irregular shapes. As you can see here, a structure can be built through the deposition of concrete material layer by layer. And that's why we exploited the concept of generative design in our study in order to reduce concrete use and CO2 emissions associated with the construction of concrete structures without compromising structural integrity, and then provide a simple method that does not significantly differ from what structural engineers are familiar with. Third, we want to provide logic that is applicable to different types of design problems. For example, we applied our method to designing simply supported beams and cantilever beams. And finally, how many architects do we have here today? I know you're an architect now. All right. How many times have you fought with engineers about your designs? So we want to help you like engineers more. And in this picture, you see like the architect and the engineer are fighting as usual. The architect thinks that their designs are just beautiful, while engineers think that the architectural designs do not really work in real life. I'm going to support you architects in this particular case, and I'm going to show you that this design did work in real life. This is a building at the American University of Beirut, designed by Zaha Hadid on another note. All right, so here's an overview of our generative design approach. We've demonstrated the logic underlying our approach through its application to simply supported beams and cantilever beams. As I mentioned before, the approach is mainly based, assume we have this cantilever beam. The approach is mainly based on dividing the beam into multiple subsections And of course, since each subsection is subjected to different loading conditions, so it's going to have a different cross-section. Now, the user may decide on the number of subsections, but generally, as we increase the number of subsections, we get more optimal solutions and more curved shapes, or like smoother shapes. Now, we should always start by setting our design goals. So what are we trying to achieve? Are we interested in minimizing the volume of concrete used, or are we interested in minimizing cost in general? And that includes concrete and steel. So what do we want to do? And then we need to define variables. How are we going to achieve those design objectives? For example, if I'm interested in minimizing cost, then maybe I want to optimize the depth of the beam. Maybe I want to optimize the width and the depth. Maybe I want to also optimize the amount of steel reinforcement. So it's up to the user to decide on how to achieve these objectives. Then we need to identify design parameters and loads. For example, what is the compressive strength of concrete, or what is the dead load we're designing for? Then we need to define the objective function or functions depending on what we're trying to do. So for example, if I'm trying to minimize cost, then I'm going to formulate cost as a function of the variables I'm trying to optimize. For example, cost as a function of depth of concrete beam. Then, of course, we need to set design constraints because we want our design alternatives to be structurally sound. Some examples of that include maximum allowable deflection or minimum reinforcement ratio that we should have in a beam. Then we run the optimization model to generate design alternatives that meet our design goals while satisfying the design constraints that we set in advance. Lastly, although the optimization model should only yield feasible solution because we've already set the design constraints in advance, it's always better to double check whether the design alternatives are really structurally sound. So we've experimented with this for designing, for the third time, simply supported beams and cantilever beams. And we tried minimizing cost alone, we tried minimizing CO2 emissions alone, and we also tried minimizing both together, focus on both at the same time. In one scenario, we tried minimizing the cost of a 4-meter cantilever beam for different increment sizes ranging from 1 meter to 1 centimeter. And as you can see in these graphs and renders, as we increase the number of subsections, we get more optimal solutions and we get smoother shapes. In fact, we achieved the best results for an increment size of 1 centimeter, where we achieved the cost reduction of 52%, about 52%, and the CO2 emission reduction reached 51% per beam. That's a lot compared to traditionally designed beams. So now let's go over some final thoughts. Although you may think that these savings, 50% savings, save only tens of dollars at the scale of a beam, only save little per beam, but the amount of savings become much more significant at the level of, or at the scale of a building. And second, the design approach we're proposing does not really differ from what structural engineers are familiar with. We actually use the equations from the ACI code. And generative design not only reduces material consumption, but also offers an architectural value. And we hope that concrete boxes become obsolete with time. And hence, architects and engineers, as they work on the same model for design purposes together, we hope that they can better understand their conflicting interests and work on them. Finally, last but not least, as a follow-up on what you said before, artificial intelligence in design should naturally follow when many other technologies such as 3D concrete printing or robotics in construction or everything you've presented about are paving the way for the construction industry to keep pace with other industries in the era of the 4th industrial revolution. Thank you very much.
Hey, thank you so much. As I said, we'll hold the questions until the end.
Should I sit here?
Pardon?
Should I sit here?
Um, we can sit there after all the presentations are done. Okay, so as you can see, there is some overlap between these presentations and the first presentation in terms of minimizing waste and so on. So it's a nice segue there. So our second perspective is from Eric Duong, who is currently an MSc student at the University of Alberta as part of the Emerging Technologies Research Stream at the Steel Center. This research aims to develop a generative design framework to optimize shear connections in buildings. Eric was first introduced to generative design while working as a co-op student at DIALOG, and has been interested in programming and how to utilize upcoming technologies such as generative design in different structural engineering applications. So I'll turn it over to you, Eric.
All right. Thank you, Dr. Driver, for that introduction. So hello, everyone. So my presentation today is going to talk a little bit about connection automation using generative design to design connections and how that can hopefully help minimize cost in steel fabrication. So the first thing I want to talk quickly about is what exactly is steel fabrication. So steel fabrication is the transformation of steel material such as steel plates, bars, angles, W shapes, HSSs into a usable product that can be used for the assembly of structures such as bridges, convention centers, catwalks, industrial complexes, and much, much more. So the pictures that I have up on the screen there are what you would typically see in a fabrication shop. On the top left, we got a plasma cutter. To the right of that, we have a few welders welding HSSs together. On the bottom left, we got a beam line that drills holes into girders, beams, and columns. And then on the bottom right, we have an angle master, which is a machine that's responsible for shearing angles and punching holes in them as well. So with all these processes put together, we can create steel products that can be used for structures such as the one we see on the right there, which is the Expo Center here in Edmonton. So where does steel fabrication play, or what role does steel fabrication play in the construction process? So the picture on the right there is what a typical construction process might look like. And in buildings, the steel fabricator can play a role as early as the design phase and will typically play a role throughout procurement and construction as well. For many steel fabricators, they'll have their own in-house engineering team that will be responsible for designing the connections for that specific structure. And it's really in the connections that dictate what a lot of the steel comes out to become during the fabrication process. So in the connection design, it's important to consider a lot of these different factors in the fabrication process in order to try to optimize and minimize the cost of fabrication itself. So let's talk a little bit more about connection design. So connection designers will often use spreadsheets or sophisticated connection design software in order to simulate and design simple to complex connections. And their main goal is always to optimize the cost of the connection. And they take into considerations of many different parameters, like the ones that I have labeled up on the screen there. And this whole process can be extremely time consuming, especially when aspects of the design change throughout the life cycle of a project, which it commonly does in the construction industry, which leaves connection designers having to redo or recalculate a large number of their designs, ultimately leading to a loss of efficiency and productivity. Well, my research in my master project aims to kind of tackle how to improve different processes in connection design and the fabrication process itself through using generative design. But before I talk a little bit more about that, I also wanted to kind of explain and illustrate what a typical connection design workflow might look like, so you guys get a sense of how long it actually takes to detail and design even just one connection. So what typically happens is the detailer will first create a stick model or a bare bone structural steel model of the structure, and then the engineer will be able to use that model along with the structural drawings in order to design the connection. Once the connection is designed, they'll sketch out the connection, hand that sketch over to the detailer, will then have to interpret that sketch and manually input all the parameters of that connection directly into the model. And this process has to be repeated for basically every connection in a structure. So you can kind of see how much time and effort actually goes to designing all the connections in a building, which makes the use of generative design to become quite desirable. So in a building project, there can be many different types of connections. There can be shear connections, brace connections, moment connections, as well as bearing connections. And the design of these connections are highly dependent on many different factors, one of which is the fabricator's preferences, as well as the design loads and framing geometry that's based on the structural engineer's design. So because there are so many different possible connections that you can have at different connection joints on a structure, it kind of lends itself well to using generative design in order to get a computer to kind of streamline that workflow for us. So what I have here is a video kind of showcasing what a parametric model of a shear tab connection might look like. So I'm just going to play the video here. Whoops. I'm going to play the video here. So the first thing we're going to see is a shear tab being generated in this beam to connection joint in Tekla, which is just the building modeling software that fabricators use. And it's a fully parametric model. So as you can see on the left-hand side there are a lot of parameters that we can control in order to change things like the plate thickness, the number of bolts in the connection. And as we're changing these, the numbers on the right there are being changed along with it. And those are essentially the capacity of the connection. So as we change the connection, everything's being updated in real time and being designed in real time. And this is essentially what a parametric model looks like. And with a parametric model, we can kind of extend that into generative design. So how generative design works is we can essentially define a lot of the variables. So in that example that I just showed, the variables would be things like the number of bolts, the angle size, the plate thickness of that connection. And we can define a set of constraints and objectives in order to get the computer to kind of efficiently search through the different design options and kind of optimize the connection for us. So to kind of showcase how this process might work, I have another video here, which was a proof of concept using generative design to optimize a shear tab connection that I did in my undergrad. And the first thing that I did want to show in this video is engineers will typically use spreadsheets to design connections, but they can also use other more sophisticated software like using the finite element method. So I just wanted to showcase creating a, the video just kind of replayed itself there. So sorry, we're just going to go through it again. But on the left-hand side there, once the screen closes it out, we have a parametric model of the shear tab, and it's being exported into a finite element modeling software called Statica. And this, I just really want to showcase that we can integrate different softwares together really easily in order to create a more robust generative design process. And now it's going to close out, and then we're actually going to see how the generative design process works for this specific type of connection. The window that just opened up is an evolutionary solver, and it's just going to start kind of going through and optimizing this shear tab. And the objective criteria that I've set for this specific shear tab is to maximize that demand that the shear tab needs to resist over that capacity to make sure that it's as efficient as possible, but still maintaining or satisfying those design code provisions. So now I've kind of showed you guys what generative design might look like for an individual connection, but what if we wanted to optimize all the connections in a building at the same time, such that they're minimizing the cost on more of a project-to-project basis? Well, so for example, what if the fabricator had a certain number of angle sizes or a certain number of plate sizes that they wanted to use first, and they had certain connection types that they preferred over other connection types at specific connection joints? Well, the cool thing about generative design is a lot of these constraints and a lot of these objectives are defined by the users themselves. So as long as you're properly defining your problem and your constraint functions, your objective functions, you can actually achieve this. And to give you guys a sense of what this might look like, I have another video here that kind of showcases what the generative design process might seem like, but unfortunately, I haven't made it that far in my research quite yet. So what we're gonna see here is not an actual design process, or it doesn't actually use the generative design process, but it'll show you what it might look like. And I want you guys to think of it as the connections are actually being designed using the generative design process. So right now I've kind of highlighted the entire structure there. Oh, sorry. Little mishap there, but we're going to just play the video. I'll talk over it again, but basically I'm selecting the entire structure here, and it's going to figure out where all those connection joints need to be. And it's actually going to design all these connections, again, not using the proper design process, but it's just going to detail and put those connections directly into the modeling software. And the main takeaway that I want you guys to have is just to showcase just how fast you can actually detail and model connections directly into the software. So you can see there's about 200 connections here, and that took about 15 seconds to run, which is pretty awesome to see. So some final things about generative design. In steel fabrication, generative design is not a black box solution to steel connection design and fabrication. You can't simply just input a few variables and expect a perfectly optimal result. There are a lot of things that happen, underneath the hood that's important for the engineer, the fabricator, the designer to understand. Essentially, generative design is ultimately a tool that can be used to help streamline and make a more efficient workflow. And it's a process that can produce a set of solutions, but these solutions still needs to be evaluated by a professional that understands that the connections have to still meet design code provisions and ensure that whatever the machine is spitting out still makes sense in the context of what they're trying to achieve. And then finally, generative design is relatively new in the world of steel fabrication. To my understanding, there's not a lot of fabricators that use generative design in their current workflow. Generative design can also find a set of optimal solution in a reasonable amount of time to minimize the cost of both connection design and fabrication. And then finally, generative design can drastically improve productivity in connection design, which is kind of what I wanted to showcase here in today's presentation. And just some sponsors with the Steel Center, and that kind of brings me to the end of my presentation.
Okay, thank you, Eric. That's our perspective number 2, let's call it. So we have one more presenter before we'll get to the questions. I hope you're remembering your questions. Write them down if you have to. Our third perspective comes from Stephen Oosterhof. He is a structural engineer at DIALOG at the University of Alberta alum, having completed doctorate in structural engineering, working with Dr. Robert Fletcher on the mitigation of disproportionate collapse in steel structures. Stephen's diverse project portfolio with DIALOG includes work on the Ice District, Kelly Ramsey buildings, as well as World of Science expansion, Cancer Center, and a number of pedestrian groups. His work at DIALOG also includes involvement in the disruptive technology roundtable, which researchers promote the use of emerging technologies that advance the practice of architecture and engineering. Stephen is an active participant in the engineering community, including regular involvement at the University of Alberta as a student mentor, research advisor, and a guest lecturer. And with that, I'll turn it over to Stephen.
Thank you very much. It's good to be here. So I work at DIALOG as a consulting engineer. I'm a structural engineer, but I also work with architects, mechanical, electrical engineers, and landscape architects and planners there. So a lot of my perspective and examples will focus on how we use generative design today in practice. And I'll try to draw examples from multiple disciplines and give you an idea of how this tool is starting to influence our design processes. So a traditional design process always starts with defining the problem. What are the constraints and parameters that inform your design? And then what are success factors that you're trying to achieve? And then a traditional design process would usually involve developing a series of options that you're going to evaluate. So I take out a piece of sketch paper or CAD and I would draw 1, 2, maybe 3 options typically. And a lot of those are informed by experience. So based on my experience, I'll frame out a bay a certain way and maybe try different orientation beams that I can't quite tell which will be more efficient. Then I'll evaluate those 2 or 3 options. We'll have a matrix of different success factors that we'll compare, just select an option and go forward. And that design process has worked very well for many years. There's lots of beautiful solutions to engineering problems that come from this fairly straightforward generation of a couple of options based on experience and evaluation. But what we're talking about today is a little bit of a different process called generative design, where the first step is the same, defining your problem. But the second step is, instead of sketching out 3 options, is actually to define a model parametrically, where anything that's not certain or defined is maintained as a variable that can be played with. And there could be 2 variables, it could be 20 in your design that aren't constrained. And then you can run that parametric model in the entire domain of all those variables to start to look at how they add value to different success metrics. And so in doing that, because it's generative and you've defined those parameters and those targets, you actually generate hundreds or thousands of models because it's being done automatically. And then the last step is to evaluate that realm and start to narrow down what are useful solutions. And through that process, you can actually discover new solutions that you hadn't considered, or because there's so much iteration going on, we will find more efficient solutions or solutions that optimize value across a whole bunch of different targets that you can set. This also requires the input of experience, both in defining the model and evaluating the outputs to have a reasonable solution. But you can kind of see the contrast between those two processes. So I think the best way to demonstrate how this works is actually to do a live demo, which someone once advised me to never do in a presentation. Probably for good reason, but I feel like when people tell you what to do, sometimes you do the opposite. So this is a blank model, and the traditional way to design options, I would start on points, connect them with lines, and then define some geometry, and that's how we do it. This is a pedestrian bridge I'm working on right now. And so I can draw any of these lines. I can't see any of what's on my screen. Oh, do you know what? I'm sharing. No, the design. And so if you look here, these are all sliders like what Eric showed you, and each one of them defines a parameter about the bridge geometry. So this is the Z component of the point at the end of the bridge. If I start sliding it, you can see the bridge grows, shrinks, and I don't know what the optimal depth of the bridge is at the end panel. Same with the number of panels. How many cross sections should I have? That's more members. Are they more efficient? Eventually it can become less efficient. So we define all these variables in this messy kind of programming language. Anytime you see these spaghetti strings, it's really just a programming language with a graphical output like this. So what we can do is feed that geometry into a finite element solver, and we can actually evaluate the stresses in all these members. And then we can feed those variables into what's called an evolutionary solver. And say, okay, we want to target the least volume of steel or the least cost, or come up with solutions that satisfy a number of these targets by varying these parameters. And so you take those parameters, and you can see what the computer is doing now is the same thing Eric's connection model is doing. It's exploring the full domain of geometries, and at each point, evaluating the target that I set here, which is least weight of steel, which is correlated to least cost. It's not perfect because connections and other things, but so you see all those plots. Each one of those is a unique combination of its variables, and it's just generating more and more design solutions very quickly. So I'm going to shut that off before it finds kind of some local maxima, but you can always go back to any of these solutions, reinstate it, and there you have that, that version of the bridge. Now, if I switch back to my PowerPoint, is that going to cause difficulties? That's awesome. I'm really sorry. Okay. Okay. Somewhere, the variables we decided to play with was where this column is located to minimize the amount of concrete needed to build this slab. And so this is a description of how that solver kind of works. So Gene A and Gene B are really just the variables X and Y where this column goes. And so it'll solve the total amount of concrete for each of those, move around and try to find the peaks of optimized solutions. And then it'll start to realize when it's finding peaks on different variables and hone in on different groupings of solutions that we can then explore. I'll skip over that. So here you can see it running, same kind of idea as that truss, it moves around, and then we can take that concept and move it to larger floor plates, more complex shapes, and try to figure out where we should put columns to minimize the material in the building. And then we can impose constraints on top of that and say, well, the column has to be located in these shaded areas, or we'll take a residential floor plate and we'll highlight all of the partition walls and say, you can only have columns there, so they're not in the way, but where should we put them? And then move it around until kind of optimize. So this, I think sometimes when you see those scripts with all the spaghetti, they look complicated and inaccessible, and this is kind of for like super programming nerds. This is a website, layoff.com. This is like you can run this on your phone, and you put in the constraints, and your design objective is the most efficient structure. So this is kind of a classical structural problem. You've got 2 points of support and a point load, and this is kind of looks like a flow net, but it's actually the most efficient kind of form to carry that load. Again, maybe this makes sense if you're 3D printing something or you have automated fabrication, but not in traditional methods. And it's so cool. I said I wouldn't try this again, but I'm doing it. Yeah, so this comes out of Sheffield, University of Sheffield. I had some exposure with them when I did some research with my PhD with Dr. Driver, but we can change the parameters to get a support here and a point load here. You got all those compression struts and this tension tie back, and this is your most efficient structure. So I didn't draw any of those lines. I input the constraints, and it generated the solution. So really cool, and really just a different way of thinking about design and how you find solutions. So I can put a hole there. It's going to have to find a net around that. Really cool. So I'm going to try to quickly show a few examples of where we use this in other disciplines. So architecturally, this is a facade, kind of a random panelization of colors and patterns. And I just picked 9 that were generated, but there was like 100. And so, yes, it's random, but you don't just want to click random and then put it on drawings. You actually want to evaluate your results, and some of them have different impacts than others. We use this a lot with sustainability. So this is a parallel axis plot. So we, for almost every building we do energy modeling. And energy modeling is influenced by things like your window to wall ratio, how many windows you have, the R value of your walls, the total energy load, the efficiency, and all together that gives you what's on the right as the output, which is your energy use intensity. But there are many different paths to get to your target. So do we use triple pane windows? Okay, so then I can say, okay, I'm selecting triple pane windows here, and it's going through all the generated options to say, okay, to make it with triple pane windows, you need an R value of this, and that's your path. Yeah. So again, it's generating thousands of solutions to find a path to the desired objective, and you can evaluate those. I won't do a live demo of how that works. I might leave it there actually with this closing comment. This is how I think about technology as a practicing engineer, as a consultant. Old technology will get you to a point, and then to adopt new technology, sometimes you have to go backwards. You have to learn a little bit. There's a little bit of pain, there's some experimentation, there's some inefficiencies to get onto the new curve of how to think about things and approach problems. But if you don't, I think that your performance on the old technology will drop off and become irrelevant. So some of these things are about thinking about how to get on that new curve. So that's the paradox of new technology. And then the caution of new technology is some of these are fads and hypes. So as consultants, you need to do controlled small experiments, be aware of what's out there for technology, test it against our desired outcomes, and throw away the ones that are just like, this will lead you there, but actually it's just a bunch of talk and smoke and mirrors. So that's my last comment on technology and how we use it. If it effectively creates value in what we're trying to achieve, then it's worth the effort to go there. And if not, throw it away and try the next one. So, thank you very much.
Thanks, Steve. If I could get maybe our brief perspective holders to join us at the podium here. We're going to open up the floor to any questions that you might have. The question can be addressed to an individual speaker or to all the speakers, but if it's all the speakers, we're going to ask the speakers to give really short answers. So just as a reminder, Eric, this is Eric, this is Fatima here, okay, and this is Steve. So if we have any questions, I think our microphone is finding its way around.
I would just like to take a few seconds to acknowledge Angela Haddad, Farah Azzuddin, Khadir Salami, and Dr. Maisa Dabaghi from the American University of Beirut. As what I presented today was a collaborative project. If you really want to know what I'm currently focused on, you can find my poster on the 6th floor. Thank you very much.
So generative design has been around for a long time, and it's still today. The tools that we have to demonstrate it, I think is absolutely fascinating and amazing, and really opening up our minds to new opportunities that obviously we couldn't even see before. So this visual management tools are great. And I'm wondering though about the methods that are used. They're using brute force methods to use exhaustive integration. So they're not particularly elegant. They work well because people found them cloud computing and fancy computing on our own computers. But this being a conference on human construction, I'm wondering if you have thought about opportunities that have been explored and being designed that actually might help take generative design a step further. And I'm thinking of two specific directions. Recognizing that we work to work with students, so of course have to start with looking at individual connections before they can look at larger systems to optimize. The question actually is just two parts in terms of how we think of systems in beam construction. So the first part is it's wonderful that you optimize the structure and that you consider fabrication possibilities as part of your objective functions, but obviously you want to build these facilities and process both in design as well as in fabrication as well as in construction might affect your objective functions. And so I'm wondering if you've given some thought about maybe more comprehensive methods to include more stakeholders' concerns and how to choose the best solutions with that in mind. And with the second question, I'll just pose it now, but we can take it on two pieces. The second question has to do with have you considered to use what we call trade-off curves in design, or to be able to use your generative designs to generate trade-off curves, so that perhaps some of the trade-offs can be made more intuitively without having to resort to exhaustive enumeration. Every question.
Maybe I can answer the first question. So one of the issues with generative design is because it is technically a mathematical approach to optimize things. A lot of things in construction aren't necessarily, cannot be mathematically defined, I guess. It's hard to, for example, in steel fabrication, when we think about optimizing a connection, we think about minimizing maybe the material weight that's being used, but sometimes maybe you can create, sometimes I guess optimizing connections can come in different forms, like maybe you can have very similar repetitive connections that you use all the time. And that would minimize cost because the guys in the shop would be doing the same thing over and over again. The guys who are erecting it would be doing the same thing over and over again. But how do you actually mathematically define that? So I guess the earlier we can get more disciplines involved and different stakeholders involved and kind of talk about these issues and try to figure out ways that we can potentially mathematically define them, would be a great way to push generative design forward, and really help broaden it and use it in a more holistic scale. And as for the second question, I've never used trade-off curves for this. Can't answer that.
Yeah, I think it's two things. What you're talking about, Eric, is trying to start to define your target functions to include considerations of how you're actually going to build this thing. Really important. And you can do that in some cases, and then in the cases where you can't define that, or the effort to define that exceeds the value it has, is actually in the evaluation of the set of options that you develop and making sure those aren't just evaluated from a single perspective. But as we move involvement of construction earlier into the design process, different approaches to look at that set of objectives and say, yeah, but we don't have a crane that can lift a piece this big, we can slice it, and this option set over here actually is buildable, and we should explore and iterate within that domain. So it's a bit of both. Right now, we're using it mostly as an early option generation concept tool, and I think you can start to evaluate that domain of solutions with a lens on constructability. I really hear your questions.
Yeah, I could add to that. If you actually think about the potential supply chain for this technology, it could be similar to precast construction. Like, for example, in precast construction, you cast everything offsite and you design connections, you ship them on site, and you install them. So we're kind of familiar with the process that we could use this technology for. That's regarding the last part of your question about fabricating this.
Yeah, this is Koshi. I'm from IIT Madras. Just wanted, in the context of what I was asked in terms of generative design and team, in target value design, it looks like we also generate a lot of options in trying to converge on the value. So, I mean, has anyone used DVD processes with generative design, or is there any experience on that? This is a general question to the panel as well as to the audience.
Yeah, not specifically. The way that we use different tools, and I'm sorry, I'm not familiar with trade-off curves, so I didn't dive into that, but it may be similar. We use something called multiple account evaluation, where you build a matrix with all of your different outcomes that you can measure, whether it's cost or constructability or aesthetics or the total embodied carbon. And then we also read each of those things. And so in building that matrix and then taking the selected options and building it out, you can see what the trade-offs are for each of your options. And that's how you can start to get through the selection process and manage this big influx of options and ideas to zoom in on that solution, which is the most effective solution to the problem, which has the least waste or whatever those targets are. I hope that answers your question. I'm not totally familiar with the field of talking about. some of those terms.
Thank you. Radhi Christensen, I'm as a sustainability director for an engineering company that also hosts architects. I agree with you, Fatima. We have some really interesting internal conversations sometimes between the two groups. And all the presentations were amazing. I think this morning was the best so far on this conference from my point of view, that's for sure. I just want to first say that what we're presenting here, we are already using. A lot of these energy design solutions are being used by engineers already to optimize the design. So I think that's really encouraging also to see that there's more research going on as well, because I could just say as well, we can cut 50% of CO2 without compromising on any functionalities, anything, any construction method, anything, just by thinking a bit more upfront. So our main solution, main challenges of it is that front loading, as we've heard a couple of times in conferences now, is a big issue. We need to be able to do that because the total cost will then actually be lower and improve that as well. And I think perhaps besides just congratulating with the good themes and the good presentations, my question is perhaps more to the audience actually, because I'm a bit afraid with all these technologies that the same thing happens, with the BIM, because at the moment we're still designing as we are using a pen and paper, even though we have all these technologies. So our industry cannot kind of follow through with processes, management, and design to actually utilize these technologies that go way back in time. And with what you're coming right now, what I see is the main challenges we have is that by adding complexity to design processes, I'm afraid that we're actually falling down to pitfalls now because we don't have processes and real management processes in the early design phases that can actually support it. So I'm just really encouraging the rest of the audience to pay attention and come up with some really good research how the community can then utilize what we just heard today, because we need that really, really seriously.
Thank you. I have one question here online, and then I was told that I draw the session to a close. Thank you for your question. The question is, for generative design, for sure trying to find the optimal color location to reduce the moment of slack. The sound was up okay. It wasn't clear, how it was working.
Sure. So what it was doing is, for every column location, it was calculating the total volume of concrete that would be required to satisfy the collection requirements and strength requirements of the slab and the columns together. And it was trying to minimize that. So yeah, that's an interesting question. So you can target a bunch of different things, but that's what that particular algorithm is.
So that's a very specific structural engineering question, but I think it does speak to how I opened the session with. It means different things to different people, and I hope that our three perspectives have brought that out. And I'd like to ask you to help me thank our three panelists.